In this video, I'll talk to you about some of the highlights in the history of hydrogeology. Now, why do I include some historical highlights in a science course? Well, I can think of several reasons. We don't often appreciate just how much our understanding in any science or technical field has evolved and changed in a relatively short time. I also have a very personal interest in exploring how we come to have the understanding we have in various fields of science. You know, science is often portrayed as a meat grinder-like process. You have the meat grinder here, you have random and unbiased observations that you pour in the top, you turn the handle of the meat grinder and out spits science theory like so many sausages. The reality is always much messier than that textbook portrayal. So it's worthwhile thinking about. And oh, by the way, some of this material will show up on quizzes and tests. I've placed an 11-page paper in the supplemental section of the website. It's this paper by Narasimhan, Groundwater from Mystery to Management. And let me just read a little bit out of the abstract. As scientists and policymakers grapple with the task of groundwater management, it is instructive to reflect on the evolution of groundwater knowledge from its initial phase of demystification at the beginning of the 19th century through successive phases of technological conquest, scientific integration, discovery of unintended consequences, and the present recognition of an imperative for judicious management. So, point number one, modern science of hydrogeology came into being during the 19th century. So let's look at some of the 19th century ideas. So, brief history, 19th century. The French needed water for their large cities, Paris, Dijon, and others. They developed the earliest quantitative hydrogeology. They found applications of heat flow theory to water flow. Henry Darcy published in 1856 his paper on gravity-driven flow. Jules Dupois in 1863 talked about basin flow in artesian wells. So there's a picture of Henry Darcy and Jules Dupois. Jules Dupois was quite the Renaissance man. He is as well known for his economic theory of marginal costs as he is for his engineering theories and flow of water in the subsurface. Here's a translation of Henry Darcy's famous paper published in 1856. Now, he only lived a few years after this, and he took early retirement in order to prepare this description of all of his work. Notice it's the public fountains of the city of Dijon. Notice that Henry Darcy is the Inspector General of Bridges and Roads, and he is describing principles to follow and formula to be used in the question of the distribution of water. Now, the major thing that he came to realize during his studies is that the flow of water was proportional to the head driving that water flow, and he built a number of experimental apparatus. Here is one pictured in his paper. It is what we would call a vertical permeameter. It's a device in which water is pumped up to the top and allowed to flow through a porous material and come out the bottom. One measures in the spigot at the bottom the rate at which water flows, and one measures with those tubes on the side the pressure of the water both at the top and the bottom. Another major development during the 19th century was the founding of the United States Geologic Survey, the USGS. Came along in 1879, and as you can see along the bottom of the page here, USGS is science for a changing world. So USGS was founded to serve the nation by providing reliable scientific information to describe and understand the Earth. a major part of the USGS mission is understanding and mitigating natural disasters. The other major part of the USGS is in the area of quantifying water, biologic energy, and mineral resources. See water right up front. Now, USGS has a mandate to carry out studies on a national scale and to sustain long-term monitoring in order to assess resources such as water. An equally important part of the USGS mandate is they have no regulatory or management mandate. Thus, they are free to give impartial science analysis. Let's move into the early 20th century. Probably the defining moment of early 20th century geohydrology was the water budget analysis of Owens Valley in order to support the idea that water could be pumped some 270 miles from the Owens Valley to Los Angeles, and that occurred in the early 1900s. So here's a picture of Owens Valley on the east slopes of the Sierra Nevada. You can see it's a fairly dry place. However, the snow melt from above comes down into the valley and can be collected. Now, building the aqueduct from Owens Valley to Los Angeles was quite an engineering marvel in 1912, and you can see in the lower picture the steam engines and wagons used to move across and undertake the work in the deserts. Here's a picture of the aqueduct today along its route and at a point in which the water is cascaded downhill. Now, discussion of the Los Angeles Aqueduct and Owens Valley is not complete without pointing out that this was a major Southwest United States water war, and I have a short section from Wikipedia at the bottom here that I'll read. The construction of the Los Angeles Aqueduct effectively ended the development of the Owens Valley as a farming community and devastated the ecosystem of Owens Lake. Mulholland and his associates, known as the San Fernando Syndicate, which included the Los Angeles Times publisher Harrison Otis, has been criticized for using deceptive tactics to obtain Bureau of Reclamation rights to Owens River flow. Mulholland, his associates, and the city of Los Angeles forced out farmers, even using violent tactics to intimidate farmers who refused to sell their land. In retaliation and protest, some Owens Valley residents sabotaged and destroyed portions of the aqueduct. The aqueduct water was crucial for the development of Los Angeles in the first half of the 20th century. So what else happened in the early 20th century? Well, it's in the area of aquifer characterization. Consequences of excessive pumping. And here in the San Joaquin Valley of California, you can see massive subsidence of the land, over 25 feet between 1925 and 1977, as a result of water mining and the irretrievable pumping of the water from the subsurface, which then caused the land to collapse. Well, the quantitative analysis of these effects was undertaken by Carl Fenterzaghi in 1923. O.E. Meinzer in 1928 looked at elastic storage in aquifers, and Tice published his analysis of the transient, that means time-dependent flow of water to wells. And these were all landmark contributions to our understanding of the quantitative backbones of hydrogeology. Now, what happened in the late 20th century? In the 60s, a number of authors began finding analytic solutions, i.e. ways of arranging equations to directly predict flow systems. As computers became more accessible in the 70s and into the 80s, major computer calculations became possible. The USGS is the source of of a major US code called mod flow, which we'll be using later in the course. There's also FE flow for a finite element flow. And the European equivalent of mod flow is Mike Shee, which was developed by the Danish Hydrologic Institute. From the 1970s to the present, contaminant hydrogeology has become an increasingly important field. Radioactive waste disposal also came in during the latter part of the 20th century, and the major shift on radioactive waste disposal was to look not at normal sorts of aquifer rocks that have a high degree of porosity and permeability, but rather to work on rocks that you didn't want fluids to flow through, i.e. tight rocks, and in the process of working on tight rocks discovered that the flow in fractures dominated and could be extensive and a major impediment to storing radioactive wastes and otherwise solid rock. In the latter part of the 20th century, the geobiological connections to hydrogeology have been increasingly important. So what's the future of hydrogeology? Well, groundwater sustainability is probably issue number one. Population growth means demand of water will grow, and water has become a defining resource for the industrial civilization. We need it for human consumption, we need it for irrigation, we need it for industrial purposes and sanitation. And the simple problem is we keep using more, and how long can we keep that up? So that ends my brief history of hydrogeology. Coming up next, I'll look at the Ogallala Aquifer in the central U.S. and discuss the sustainability concerns associated with it.